Hey friends, what's up? I hope everyone is doing great. I welcome you all to my web series of machine learning projects and all the other cool stuff that are out there in the market. Our mission is to have machine learning reachable to as many people as possible. This is RK and a very warm welcome to everyone once again. So, in this series of ML videos, we'll be talking or rather taking a business objective and then try to solve it step by step using the ML algorithms. We are primarily going to use Python. Unfortunately, in this series, I won't be able to cover the basics of Python. I hope that's clear. If if you require any videos on the basics, I'll do videos on it based on the demand from the audience. So please comment and provide your suggestions as well. So without further ado, let's proceed with what is it in for today. So can I predict a bike demand? Yes, absolutely you can. It depends on what is the data set that you have, what kind of algorithm or machine learning that you are trying to use. And so in this um, case study, we are going to learn how we can predict a bike demand. So what's a problem statement that we have in place? So the bike sharing systems are a means of renting bicycles. It's either through membership, rental, and then it is run via a network of kiosk locations. The company B-Cube is a bike sharing system which makes bikes available for users on a short-term basis. And the company suffered some dips in their revenues in the ongoing pandemic. That's where they are trying to understand the factors that causes the demand on the shared bikes. So what is the objective that we are trying to achieve? So there are two objectives here, as you can see here. Um, the company wants to find which variables are significant in predicting the demand for the shared bikes and how well those variables describe the bike demands. And predominantly, you're going to cover on all these steps while trying to create our model. So first thing is we are going to understand the data. Here, you need to load the data and understand the features present in it. So in a EDA, what really happens is we are going to identify some skewness, whether the data is normally distributed or if there are any outliers on the machine learning models which are sensitive to some of the outliers, which may cause some potential problems to our model. Also, if the value of any independent features are skewed, that depending on the model, skewness may affect model assumptions or may impair the interpretation of feature importance. Um, the third one is the train test split. We will choose 80-20 or 70-30 based on our needs, um, which is 80% of train data set and 20% of test data set. In feature engineering, we are going to select the features and by running repeatedly some of the stats model and making sure that the model doesn't overfit. The last one is on the model building and hyperparameter tuning. This is the final step at which you can try different models and also fine tune their hyperparameters until you get the desired level of performance using the model evaluation technique. All right, so let's get into the coding aspect of it. Um, Here, like I said, this is the business objective that we are trying to understand. So Bcube wants to understand what the variables are significant in predicting the demand and how well those variables describe the bike demand. So as I previously mentioned, we need to understand the data, do some EDA, and then do some splitting of training, training and test data set, and thereby trying to gather the features that are um, more um, that provides more impact to the model, and then finally fine tuning those model using hyperparameter tuning. So the first step is to load the necessary libraries. Like so these pandas, numpy, all can be installed. I mean, I have already installed in my system here, so it's if you don't have it, then you can use pip install pandas and then pip install numpy. It should pretty much do the job. And as well as scikit-learn usually provides a lot of models or pre scikit-learn provides you a lot of libraries that can be used to create your regression models. So why we are choosing a regression? Why not some other classifications or um, well, we'll come to we'll look into those details when we go through this exercise. So what we are doing is we are loading all the required libraries: pandas, numpy, matplotlib, and seaborns. Matplotlib and seaborn are basically used to plot your graphs. And from scikit-learn, we are trying to import some of the libraries like linear regression, min-max scaler, train test plate, RFE, R-square, R2 score. So let's. I'm not going to go into depth of each and everything. As we go through the code, I will try to explain more and more in terms of why why we are doing this and what needs to be done. And the stats model dot API also provides some detailed statistical analysis, which is helpful in which helps us in taking some decisions around the feature importance. And the import warnings, which filter out some of um, basically some set of warnings, which I generally keep it. Otherwise, you will have a lot of other general warnings that comes up and unnecessarily um, uh, deviate your attention. And VIF is, I think VIF needs to be here. I'm sorry about it. So let me paste it here. So VIF is another important factor that we will also try to understand today. So when you do a shift enter, it basically runs. So you can use either Jupyter Lab or Jupyter Notebook. It's up to you. So after you import the necessary libraries, what we have to do is reading and understanding the data. Again, we have the data and also the Python, the notebook file. I've loaded that into GitHub. So and also have provided the link in the description, so you can always pull it up and then try it out from your side and also tweak whatever is required from your end. So this notebook is self-explanatory, and I'm also providing with the required comments. What are we trying to read here? The day.csv file contains all the relevant. So I'm executing the file. It loads the relevant file with all the relevant information. We'll get into those details one by one. So let me check what is the rows and columns. So we have 730 rows and 16 columns, predominantly from 2018 to 2019. And what we have in the bike info. So these are all your columns. So what are the columns that are helpful? So instant is nothing but the record index, nothing much. DTE day, it's the date. And season, season is given in numeric format, which is 1 2 3 4, and 1 corresponds to spring, 2 corresponds to summer, 3 corresponds to fall, and 4 corresponds to winter. um, the MNTH is nothing but the month. It's again a numeric value, which is again 1 to 12 from January to December. And holiday is again an integer, which is either is a holiday or not, whether it's 0 or 1. The weekday, it's the day of the week, either it is Monday, Tuesday, Wednesday. Working day, whether it is a weekend or it's a non-weekend or a weekday. So if it is working day, it is 1. If it is weekend, it is 0. And whether it is nothing but it is categorized as uh, 1, 2, 3, 4. Again, it's a numeric value that you see. It's either 1 is nothing but the clear, only a few clouds and partly cloudy. 2 is nothing but it's misty, little bit cloudy, few clouds here and there. 3 is light snow, light rain. 4 is heavy rain, ice pellets, and thunderstorm. And temp is temperature in Celsius. A temp is the actual temperature. Humidity is HUM is humidity. Wind speed is again it's nothing but the wind speed. Casual and registered are nothing but the casual users who have registered for the bike demand. Unregistered users are the users who have registered for the bike. And CNT is nothing but the count of total rental bikes, including both casual and registered users. Okay, let's deep dive into this again. So what does describe tells us? The describe function provides some basic statistical details. For numeric data, the results index will include count, mean, standard deviation, minimum 25. So by default, the lower percentile is 25 and the upper percentile is 75 and the median is 25, the 50 percentile. We have everything as a numeric value and we are able to get some um, good detailed statistical data. All right, so looks like there are no missing values and the data looks pretty good. Okay, which is also notified in the info tab, wherein it tells you all the 730 rows are non-null. All right, going further, visualizing the data. So this is an important step wherein it helps us to take some decisions around visualizing the data and drop the columns that are not relevant to the analysis. What we do is we take some factors like the instant temperature, actual temperature, humidity, wind speed, and the total count of rental bikes. That includes both casual and registered users. So let me run that. What happens is it gives you a bunch of plots. The variable of importance here is our CNT against the other variables like instant temperature. So as you can clearly see here, temp and let me zoom in a little bit. So the temp and a temp shows you there is a positive correlation. So when the temperature increases a little bit, the number of users or number of rental bikes is also going up. Whereas the humidity and wind speed, it is kind of a negative correlation, as you can see here. So which means that if wind speed or humidity increases, there is a less demand of the bikes. So okay, so we got some clue around this. Let's see um, what what do we need for this model and what we don't. So based on this, the distribution of temp and a temp looks similar. Hence, we can remove either one of them. The column instant and DT date doesn't have much information to provide. So what we'll do is we'll drop instant DTE date, casual, registered, temp. So I'm keeping actual temperature, but the temp is taken off. It causes some correlation issues, which we'll discuss in a later part of this. Um, so if I press it creates a cell above it. So what I wanted to check is, let me see the shape of it. So as you can see, the column number of columns have reduced by 5 and there are 11 columns totally. So if I press DD, it takes off that cell, and DD is for deleting it. Um, Data preparation, what are we going to do here? So we are going to prepare the data for further visualization. The variables like the month, season, weekday, weather set are all given in terms of numerical values. Month is spanning from 1 to 12, season is 1 to 4, weekday is 1 to 7, weather set is also 1 to 4. So we are going to categorize or basically for us to derive meaningful data out of the visualization plot, let us assign some string data types. You understand what I'm saying, right? So for example, in the month, it's given as 1, 2, 3, 4. So what we are going to do is assign some meaningful names to it and then see the visualization and take some necessary steps. So I map 1 as Jan and likewise 12 as December. I run this and then try to okay, so there are 62 instances of May, likewise, and then February it is 56 instance. It's all converted. So the month field is converted into a string information with all this data. And likewise, the season is also converted. So I'm assigning 1 as spring, 2 as summer, 3 as fall, and 4 as winter. Weekday, since the weekday starts with Sunday, I'm assigning 0 as Sunday and 6 as Saturday. Weather set. So they tell me that 1 is nothing but the clear. It's little bit of cloud, so I just gave some name to it, clear. 2 is little bit of cloudy, so that's I gave it as misty cloudy. And third is little bit of snowing and all this. It's a light snow. And 4 is heavy snow, pellets and thunderstorm. So I gave it as a heavy rain. So perfect. Until now. So let's try to run this, visualize this categorical variable. So what I'm trying to do is I'm creating a subplot. So basically I have uh, 3, 4, 5, 6. So six graphs that I need to generate. I'm doing a subplot of 2 rows with 3 columns. The graph is going to be created using a box plot. As you can see, it has generated a nice box plot. And what is that we are trying? What is that we try to infer from this? From the month against the demand, we see that January seems to be of less demand compared to other months, whereas June, July, August, and September seems to have more demand compared to other models. And in the season, the demand of bikes is high during summer, which is pretty much obvious as you can see here. This is in the US, so summer is typically July, August, September. So, which is given in our second plot as well. The demand of the bike, okay, so it is high in summer and fall and winter season, the demand is less. We come to the weekday, the demand of the bikes is the same during the weekday. On the weekend with slight high during, I mean in Thursday it is little bit slight high, but it's not really differentiable. What happens when the weather is cloudy, or I mean if it is snowy, the demand is less. That with a clear weather, we see the demand is more. Year is indicated as 0 and 1. 0 is nothing but I think I didn't change this for some. I think you can always edit this 0 as 2018 and 1 as 2019. So in 2019 compared to that 2019, the demand is more. And the demand of bike is less during holidays and compared to a non-holiday, right? So that you can see here. As a non-holiday, it's the demand varies across from 0 to higher numbers, whereas the median as well is, I can see that during a holiday it's less, whereas in non-holiday it is more. Perfect. So I hope this is clear until now. Um, so there's a next step. What are we trying to do is creating some dummies for the categorical variable. So um, with the categorical information in the data set, um, it is not possible to derive the regression equation. So from these graphs and based on the data set that we see, let me try to visualize one more time. What is it contained of? So it gives me pretty much uh, the feature information. More of it is in numerical values. I mean, we'll talk about the object because we converted that into a string information, but we will also convert that. So what exactly are we talking about? We said we are going to use linear regression. So with linear regression, we will need to understand two different types of regression here. Let's go to some basics and understand. So in a simple linear regression, we try to uncover the relationship between dependent and independent variables. So the dependent variables is nothing but the response variable that you see as y, and the independent variables are nothing but the explanatory variables which explains the behavior of the response variable. So y is equal to mx plus c, where m is nothing but here beta, it's a slope, and c is a constant or the intercept. Here it is denoted by alpha. This is against the marketing budget and sales. So as the marketing budget increases, the sales increases. This is pretty simple with one variable, right? So what happens when there are multiple explanatory variables, x1, x2, x3? Um, which becomes a little difficult because you have to see this in a multi-dimensional way, and it really makes it impossible for us to visualize that. So that's where our algorithms or the machine learning algorithms are coming into help. So the as you can see, the equation yi is equal to beta naught, which is nothing but the intercept, and beta 1 x1 beta 2 x2 beta p xp. Likewise, so let's consider for from our previous example to this, the marketing budget might consist of putting it against TV ads, newspaper, digital marketing, and due to that, what is the increase in the sales? So um, they, since because we are having multiple features here, it becomes a little difficult to visualize. Feeding this into the algorithm gives us pretty much details into which factor explains or have more impact on the dependent variable, which is nothing but the sales. I hope this is clear. So we are going to use MLR, which is multiple linear regression in this case, against our case study. All right, so coming back again, as you can see, there are objects that we created. So having a categorical variable in dataset, it would not be possible for us to derive the regression equation. So we need to convert those categorical variable to numerical variable via dummies. So what exactly is a dummy variable and where is this used? Dummy variables are useful because they enable us to use a single regression equation to represent multiple groups. In our case, for example, if you see, it is highly impossible for us to derive multiple single regression equation, one for season 1, season 2, season 3, likewise. That's where our dummies are going to help us here. This means that we don't need to write separate equation models for each subgroup. The dummy group or the dummy variables are going to act like switches that turns various parameters on and off in an equation. The pandas provides a beautiful function here, get dummies, to create dummies for the categorical variable. We can also drop the first variable. So as you can see here, for our case on the seasons, we have 4 seasons that we have created, right? So let's go back and see what are the 4 seasons. So we have spring, summer, fall, and winter. So what we try to do is in spring, summer, winter, and fall. So fall is taken off because uh, dropping your categorical variable is possible because if every other dummy column is 0, which means that the first value would have been 1, right? So if it is in this, we are not able to see other rows, but if you for example, you take in this case the spring is all 0, summer is 0, winter is 0, which means obviously the fall is kind of 1. And so it makes sense for us to have lesser number of variables in our equation rather than offloading. So this explains the feature variable as well. So let's, since our focus here is on the bike demand regression analysis, we are not going to go in depth of this subject, which is dummies. And if you require, please comment and I shall create a new video especially focusing on this subject. Let's run all the other code and then see. Yes, it's perfectly run. Let us now concatenate the dummies into the main data set, the bike um, with the season dummies, month dummies, weekdays dummies, weather set dummies. Perfect. This is all concatenated, and we have 33 columns. Since we are seeing the head, it is just showing as a 5 rows, but I mean, let's see the shape as well. Yeah, the rows has not changed, which is still 730, and the columns have increased to 33. This is because of the dummies that we have in place, right? And again, so the original, um, we'll drop the original categorical variable, that is the season, month, weekday, weather set from the bike data. So it doesn't make sense to have it because we have dummies in substitute of that. So I mean, it shows here 29 columns, so 5 columns, 33 minus 5, 29. Yeah, perfect. So until now, I hope everyone is clear. As a next step, so once we have the clean data available, we will now split the data into train and test data, rescale the data, and then visualize them again to see if any correlation happens. Here, please remember that we are not going to do the rescale and visualize on the entire data set, okay, as we are going to inadvertently bias our model. That's the reason we are splitting the data into train and test. So the train test split is a function in scikit-learn for splitting the data arrays into 2 subsets, for training data and for testing data. With this function, you don't need to divide the data manually. By default, scikit-learn train test split will make random partition for the 2 subsets. We are using train as 70% and test as 30%. However, you need to specify a random state here for the operation, right? So let's see, we are going to get 70% of the 730 for the train, 30% of 730 for the test. Let's execute and see. Perfect. So 70% of 730 is 510. As you can see, the columns are not reduced. It still remains the same. What our main focus is to get the um, rows split into 70-30. So the next step here is to rescale the data set using min-max. So what does min-max does? Well, it scales all the data features in the range of 0 to 1 or else in the range of -1 to 1. So why do we need min-max scaler? The variables that are measured at different scales do not contribute equally to the model fitting. and models learned from that might end up creating a bias. For in our earlier example, we saw um, the sales is in millions, whereas in the budgeting is in thousands. So that kind of variance in terms of uh, measurement create a bias. So to deal with this potential problem, feature-wise normalization such as we are using min-max scalar are used prior to the model fitting. So if you notice it carefully, the variable list that we are picking are a temp, humidity, and wind speed. This is because the other features are already binary, right? It's either 0 or 1 that you can see here, except for atom, humidity, and wind speed. And let's right now leave out count, which is nothing but the dependent variable, which is y. We are talking about x1, x2, x3. So we are taking these three and then trying to convert them, right? So let's try to run this. Well, so as you can clearly see, um, let's take example of a temp. So um, what's the difference? You see the maximum is 1, the minimum is 0. So all these a temp, humidity, wind speed are converted in the range of 0 to 1. Okay, so once we are able to normalize, we will visualize the correlation of the data. Okay, and check if we can provide any way valuable insights into our model. The feature of our interest is the count variable. Um, so let's first run this and see what it gives. It takes a little bit of time, not much of time. Here, let's take what's our feature of interest is a count variable. So um, let me let me maximize this a little bit, and that gives you a clean indication. So feature of interest is the count against which we see year is 0.57, which is a good positive. So as you can see here, the scale and the scale of thick green is 1, which is a heavy high correlation, and thick red is negative correlation. So the count against year is 0.57. Okay, a temp is 0.64, which has high correlation. um, However, you can see, I mean, you see here 1, which is nothing but the count versus count is typically 1, so all the diagonal will be 1. Rest of the other um, features are kind of negatively correlated. So let's see, do some scatter plot against a temp and okay, perfect. So I think we have seen that in the beginning as well. So um, this is a pure positive correlation that happens here. So what is our next step? So the next step is to divide the training data set into X and Y as so that as we have seen previously, our feature of importance is count variable. We will assign the value count to Y train and the rest of the uh, data to X train. So let's execute this, having count, and the X train has the rest of the other. So um, as we saw previously, there were 29 columns, and now popping out count and gives us 28 columns. Well, this is good. What is the next step? We are going to introduce RFE. RFE is recursive feature elimination. What is an RFE? It's a feature engineering that helps you in extracting hidden insights and the underlying structure of the data by modifying, combining, extracting, or selecting features that are less prone to overfitting. This would help you to choose the features that will be used to train your model. So here we analyze the columns. So the columns again, this is the same column except for CNT. You will have the rest of the other columns. What I did here is to I try to get some 15 predictor variables. So the code is simple in terms of initiating a linear regression function and then trying to fit the using our train data, which is split again into X train and Y train. Using RFE, we then try to arrive at the 15 predictor variables. Using RFE technique, this is the simplest way to arrive at the desired set of features. Um, so we will look into the fine-tuning, the process of extracting the features from those 15 using a manual method. Let's try to run this. So the X train, okay, let's see. Okay, it has generated an array of true, false against the column. So for example, year is true, holiday is true, likewise, all these are true, false. So it's highly impossible to correlate one by one. I mean, if it is a 28 columns, it's pretty easy to map. But what we can do is trying to map the columns against the true factors. So as we can see here, year is true, and whereas let's see one case August, it is false. So it says the models the function RFE eliminates all the other false information and then tries to give you the topmost 15 variables that are impacting your independent variable, that is the count here. And let's try to get those columns that are assigned with true and get rid of the other things. So we then assign those columns back to RFE, extrain RFE, and then extrain RFE contains only 15 such columns that are going to impact your model as such. So from this on, what we are going to do is fine tune our feature using a manual elimination with the help of um, detailed stats model. As we saw in the beginning, SM is going to give you a detailed statistical model. You might have noticed that we are adding a constant here. So what does a constant do? By default, the stats model is going to fit your line passing through the origin, that is y is equal to mx. um, it's going to not provide you with the intercept. So to do hence you need to use a add constant so that it also fits an intercept um, to give you mx plus c kind of a thing. So let's try to run the extrain RFE that we generated earlier. We are adding a constant and then trying to fit that model. So here there are a couple of things that we need to understand. One is uh, p-value. The other one is going to be the VIF. So let me project and see if we can go through that data. Okay, so the p-value that comes out of those stats model, you might have learned about the null hypothesis and alternate hypothesis, right? The H naught here says that the variable is insignificant, and alternate hypothesis H1, the variable is significant. So if at all we get a p-value less than 0.005, which is nothing but 5 percentage, we reject the null hypothesis, which means that the variable is significant. If the p-value is greater than 0.05, then we say that we fail to reject the null hypothesis, and then we say that the variable is insignificant. So what we are trying to identify here is the variable significance. So we will need p-value less than 0.05. I'm also introducing a new topic, VIF. So VIF is nothing but the variance inflation factor. This is a measure of the multicollinearity in a set of multiple regression variables. So um, one variable can be explained by different variables. So a high VIF usually indicates that the independent variable is highly correlated with the other variables in the model. For example, in this exercise or example, we see that the weight is the weight has a high correlation against blood pressure. The body surface area is also having a high correlation against blood pressure. So, and as well as the weight. So, the weight can be explained in terms of blood pressure. So either we tend to keep either one of the variable, otherwise it's going to bias, or you don't know what exactly is going to cause your model to behave improperly. Um, in this same regard, we are going to see what is a correlation versus causation. So don't confuse a correlation with a causation, right? So they are not caused by each other, they are caused by weather factor. So if you try to read in between lines, you can always say that okay, as the ice cream sales grows, the shark attack also increases. It doesn't interpret that way. So let's get back to our equation here. What we have arrived at, um, the so we said two things. One is the p-value that you can see here, and the other one is a VIF. VIF we are yet to generate, but as you can see here, the R square is a 84.3 and adjusted R square is 83.8. So the difference between R square and adjusted R square is that adjusted R square. What does an R square mean? R square measures the goodness of the fit of the regression model. The higher the R square indicates the model is good, while the lower the R square, the model is not a good fit, right? So the difference between R square and adjusted R square is that adjusted R square considers and consider different independent variable against a model, and R square does not consider it. So the more independent variable grows, your adjusted R square value goes down. So you have to be a little careful in that. See the deviation between R square and adjusted R square and then take a call accordingly. In this equation, we see that the p-value that are greater than 0.05 is of our prime importance, and working day, the Saturday, Sunday. So we are not going to focus only um, on the p-value alone. So we are going to focus on the VIF factor as well, which is going to tell us the multicollinearity. We will pass on the extrain RFE and then try to see the VIF. So this is the simple one-liner that helps us in getting the VIF. The descending order. So VIF of humidity is 36.8, working days 35.8. So in this case, we see that the Sunday, we saw Sunday was having a high p-value, and it is also having a high VIF. So we consider both of them in tandem and then try to eliminate Sunday here. What do we? Okay, I'm just dropping from extra in RFE, and then it's a pretty manual step that you have to do from now on. So again, adding the constant to the newly created, extra in SM, and then trying to fit it against white train. You see the R square and adjusted R square are more or less the same. You might have seen that it was 84.3, 83.8, and yeah, it has in fact 84.3 and 83.9. See, as we reduced a variable, the adjusted R square is also increasing. So there is no impact on the R square. As you can see, it is still 84.3, but we will look into the p-value if it. So working day, the Saturday has a high p-value. Saturday has 2. So let's take off the high p-value from the data. The data set, we are after removing the high p-value of Saturday, uh, we'll again try to generate. As you can see, the R square is still 84.3 and adjusted R square is 83.9, which means that removing Saturday from the model doesn't have any impact on our R square and adjusted R square. Let's see if there are any other p-value which are greater than 0.05. So pretty much is, and this is clean. Sorry, the VIF is higher in terms of humidity, so it's 26.07. Let's try to remove humidity from the um, data set, um, and then run again the stats model. um, 84.3 to 83.4, it has reduced by 1 point, nearly zero point 0.9, whereas more or less it's coming to a um, in equal lines, R square and adjusted R square, 83.4 and 83, which is good. The p-values are less than 0.05, which is also very good. VIF generate. So VIF a temp is higher. Uh, so let's stop. Why? Yeah, September though, I mean, we are trying to look at again the 0.05. This is coming closer to that. So we don't want ideally anything to be closer to 0.05. So we are removing September from the equation or the data set. Let's try to see. I mean, you can stop there. It doesn't really impact any of you. You can still retain your September, but I just wanted to make it a little bit more cleaner. So I'm trying to remove. As you can see, it doesn't have any impact to removing September from our model. Doesn't have any impact to the R square and adjuster. It still remains the same. And we'll again run the VIF and see. Uh, but before that, holiday is again coming closer to 0.05, so let's remove holiday as well, um, and try to generate the equation. So it reduces by zero point 0.2 or something, but that is okay. So we still have R square and adjusted R square closer to, and we'll run the VIF. Everything are less than 5, and your p-values are all lesser than 0.05. Very good. We see that all the p-values and VAF are within acceptable range. We shall go ahead and predictable, right? So the last is X-train SM, that can be helpful to predict. So LM was our model, and then we pass on the X-train SM to generate the Y-train pred. All right, so far so good. So the next step is to plot the error term. There are 4 basic assumptions, right? In the error terms that we observe. So we need to have a linear relationship between x and y, which we have done that, and we see that there is a linear pattern. We are good in that. Once we have the error term is nothing but your initial value, which is y, and the predicted value, which is y pred. So if you try to do a distribution, it should show a normal distribution, and it shouldn't show something similar to um, the. If it is not normally distributed, then it negates one of our assumptions of linear regression. And the error terms, there is no significant visible pattern. For example, if you see here, the error terms increases as we increase on y, so which is showing some kind of pattern. This is not right thing from our model. So this again negates the model assumption. So the last one is that homoscedasticity. Here we see the has a constant variance. I mean, it is constant against your line or the equation, right? So so the variance keeps on increasing here as we increase on the x direction. So this is not this again negates our assumption of linear regression. So um, enough of our theory, and let's see if any of those are if our assumption still stands valid. So the error terms are arrived by using um, actual minus predicted values, and we do a prediction. I mean, we do a distribution plot um, on the residuals or the error terms. Um, so it gives a nice normalized figure here, which means that one of our assumption which talks about it should be normally distributed. So this is good. We'll also see the homozygosity factor. Across the regression line, you see that it is equal variance across the regression line. So um, there is no increase in the variance as we go. So this also proves the homozygosity. We will also verify on the correlation. As you can see, there is no uh, does not have any pattern, and we classify that this model is good. All right. So as we see that we are good with the following assumptions: the linear relationship between x and y, the error terms are normally distributed. Yeah, right. And then the error terms have constant variance, and the error terms are independent of each other, doesn't show any particular model. So hence we qualify that the model arrived is a best fit model, and we can proceed with the tested data set. So we'll apply this on the test df underscore test, which we have already taken out, which is the 30 percentage. Um, let's try to see what is the shape. Yeah, 219 rows, and we have 29 columns. So uh, the columns here are, I mean, we have every column. Okay, let's try to describe and see. Okay, well, so what we see is it's we need to do some scaling around. So we'll need to apply the scalar dot transform on the df test. What does it provide? It provides you value between minimum value is 0, maximum value is 1, likewise, right? And so this is good. And we will divide the test data into x and y. So likewise, what we did for train data, we'll also pop the count to y test, and the rest of the columns into, yeah. So before that, I think the X-train RFE, which has which we preserved the columns of our interest assigned to our uh, the X test. So X test is going to have only these particular columns, and using that we will need to add a constant for the same reason, and we will use that to predict spread. And also we will so once it gives a y-test spread, we'll need to evaluate the model and check its goodness of fit. So we'll try to plot and see. Okay, as we can see, the y-test and y-test spread, they are uh, linear. The normalization, okay, it's normally distributed. Perfect. Our model is good. And then the last thing that we have wanted to check is on the R square. Like we saw, it should be around 83. Yeah, it's 83 and 79. So the difference between the train and test data is less, which is a perfect or a decent model that we can say. So this is our model that we have created. So good job, guys. I think this is how uh, typically a model is arrived at using uh, the machine learning algorithm. So we have used here MLR. Likewise, you can use a number of algorithms are out there in the market. So uh, so this is a simple just for the basic start. In future videos we are going to cover different sets of algorithms with the different complexity or raising complexity. So good luck, everyone. Please do comment your observations, or let me know what you think about this and what needs to be changed in the upcoming video. All right, have a great day, and this is RK signing off. Have a pleasant day.